So I'm here to talk about a small project that I did over Christmas. Just yeah, something fun. Automatic toothbrushing timer. So like a practical gadget maybe. This is an example project that I developed. I am a maintainer of a machine learning tool, a TinyML library called emlearn, which also has both a C library and also a MicroPython library. And here we're using the MicroPython library. So as you know, most TinyML tools, there are kind of two typical aspects. You do the training on your computer, and then there's the emlearn Python package. So you can do your model creation in Python, use standard libraries such as scikit-learn or keras to train your models. That's like the standard process. You don't have to care so much about the tiny aspect. And then there's a one-line function that we provide to export this to device code, which can either be C code or it can be a model that can be loaded into MicroPython. And then there's the second aspect, is the runtime library that goes onto the device. And one cool thing I really like about MicroPython is that it has the ability to have C modules. So they're fast and small in size, but they can actually be installed at runtime, so onto the microcontroller. So you can do mip install and install one of the emlearn modules. It's really powerful concept and very convenient. And I think it's very important to have accessibility in mind, and it makes everything simpler when you can do the runtime install instead of having to do a full rebuild. And it's very fun when it's so accessible. So there are a set of examples in the emlearn machine MicroPython library, such as like very standard tasks like activity tracking. There is some about sound level monitoring and also image classification. But these are using standard data sets. So we wanted to, to try out and have some examples where you do custom data sets, because that's, I think, the most interesting task is when there is no data, because you have a new task, you have a novel task, like the tasks that were described here today and related. That's the most interesting parts of TinyML. So yeah, the idea I had was a automatic toothbrushing timer. I have it with me here. Hope you can see me. So if you are actively brushing, it will count you up. But then if you don't finish your 2 minutes, it will eventually give up and say you didn't do a good enough job, try again. And then you need to repeat the same thing all the way to 2 minutes. I did a cheat and set the configuration lower now. And if you continue, it will play a much happier sound. Because if you don't brush your teeth thoroughly enough, of course, the effect will not be so good. And this is a real problem in society. People are not really good at brushing their teeth. Maybe this gadget can help. At least it was very fun to build. So the parts that are in this is, of course, an accelerometer. So we're tracking the active time. So if you just had a button, you would press it to start and it will count. It would be I'd find it quite annoying to use. So we want to detect that automatically. And we're using machine learning. And then it's nice to have audio feedback. First, I thought you could have it on the screen, but I realized you're not going to be wanting to watch the screen on your device when you're using it. So audio is much more practical. And yeah, I used for this first prototype a M5 stick +2 from M5 Stack. It's a nice complete unit. Has battery and also screen, stuff like that, but most importantly, a buzzer and an accelerometer, and also a microphone, which is not used in this project. But it just enables you to do everything without having to solder and so on that. So it's very easy to replicate and prototype. And then there's software wrote in MicroPython. It's around 500 lines total. That includes some tests and things like that. And the software is structured as you see at the bottom. So the innermost core is some data processing, which is feature extraction, and then the actual classification on the incoming data. To the left, there is an accelerometer driver that you need to have to read data from the accelerometer. And then to the right, there's some state machine and some way of producing this output sound, so that there's like a playback of notes, which is I found some nice example code for that. And the state machine, actually, even though it's a simple type of project, you need to take consideration the things shown on the screen. And the happy path here is like you start at the left, you start sleeping, so the device is always active, but it's in a low sleep state. If there is any kind of motion, no matter the type, it will go into an idle state and then check more actively, like, are we actually brushing our teeth now, or is it just some random variation, or someone is moving the object or something like that. And if you're brushing, you go to the brushing state, and then that's the time that you get points for, that you count up. And if you hit your 2 minutes, then you are done, and it plays the happy sound. But then if you don't, you will go back, and eventually, if there's a timeout, you will get into the failed state, and then it will return to sleep. So even in a simple project, it's nice. It's smart to draw a state machine diagram, because in order to handle these various edge cases. And data collection, I recorded myself. I used then both the device itself, so it's representative data, the accelerometer. I collected it using the tools that we provide in emlearn. It can store the data directly on the flash internal. And then I also recorded myself while I was doing toothbrushing on a phone, so that I can use that as the ground truth for when I'm actively brushing versus doing other things. Because I realized that even though you think of yourself as brushing your teeth, you might be doing other things, like rinsing your toothbrush, or maybe someone is talking to you and you're responding to them, and you're not actually brushing teeth. There's just activities that happen related, and those we don't want to count. And importantly, we have two data streams, one from the device, the accelerometer data, and then the video. So I did a simple synchronization protocol in collection, where I tapped the device like 5 times in the start of a session, and then 5 times at the end of the session, so I can find this in both data streams and synchronize the data. And then I label the data using the video with the Label Studio. So it's a quite nice tool to label this kind of data. And then, because I know the data is synced, those labels can be transferred onto the sensor data. And there are tools as well for that in the repository. So both to create the correct format in and out. The machine learning pipeline is quite simple in this case. To the top right, you see the feature extraction. It's just very simple statistical features of short windows. I believe they're around 1 second. And that is classified using a random forest classifier, so a decision tree ensemble. And there is a training script as well in this example repository, which can be used for other tasks, such as human activity recognition, like the typical, like what are you doing with a smartwatch, or for example, exercise tracking. There's also an example of that there. So you can plug it in by declaring a data set, which is shown on the almost top right. And then you just run this pipeline, it spits out a model. And this is then using emlearn tool under the hood to produce this model.csv, which is a serialization of our random forest, which you can load on our device. So that's the basics of how it's done. Please feel free to ask more questions. And the potential improvements. So like this is a prototype now, and it's a fun gadget. But if you would think about this more as a closer to a real product or a real tool, I think the device should be much more affordable and much more compact and easier to get started with. Right now it's using zip ties, which is a bit annoying and a bit too permanent. So I'm prototyping some much simpler thing that you can easily take on and off, and that is smaller and more compact, so it's less in the way. That means the electronics need to fit. So another project I'm working on is like a $1 machine learning board, where the bill of material is under $1. That's shown to the right. And I will try to port this simple application to that board, which is a small microcontroller. And then we would be using the emlearn as a C library instead of MicroPython, because this that chip cannot run MicroPython. And it's been sponsored by PCBWay, the recent PCBs that we got. So that's nice. So that's what what we'd like to see to take it next. Yeah. So summary: emlearn MicroPython aims to make TinyML very easy. MicroPython means all your application code can be done in Python, so it's very practical and quick. We have then these examples that are good starting points, and you can easily use custom models for such a niche application with a few hours of data collection, run an existing pipeline, and you have at least a proof of concept and possibly a solution for your task. So thank you very much.
Great presentation. Well done, John. Any questions for John? We have had a presentation of the emlearn before, and it's pretty interesting. I think everyone should check it out. But good on you doing the toothbrush. That's kind of making it, real, and you're going through the steps. Any questions for John, first of all?
John, you mentioned low power. So how much low power would it be?
Oh, we'll see exactly, but this task, in the low power state, you would basically turn off the microcontroller and let the accelerometer run. So those do just like 5 microamps, and because you can do low sample rate. And so I think 10 microamps, 20 microamps, something like that in the low power state. And then it depends, like how much are things moving around? How often do you go into a slightly higher state to check what is maybe going on?
And my second question would be, do you think you can even kind of classify which part of the mouth you're brushing?
Yes, I think it's quite possible. Actually, I first tried to find a data set for this task, and I did find one, and they researched this problem. However, somehow their labels were not clearly available, but they classified into something like, I think, 16 different positions.
Yeah, something like that. Yeah.
So so what you might want to do is to ensure that not only people are just doing the motions long enough, but they're actually covering their whole area. So it looks to be possible. They have the research paper showing that.
Are there more questions? I really liked today because normally we have a presentation where everyone's excuse me, using Edge Impulse, and now we're starting to branch out into a lot of other methods to get the machine learning models on the microcontroller. So I found the presentations really interesting today. We are very close to our time. I really appreciate everybody with their great presentations and the length of them. Any other questions while we finish up?
I have a quick question for John. It might not be very relevant, but I wonder if you just simply keep swinging the brush, would it still detect that as activity, or would it require some sort of friction? Because I know accelerometers can be sensitive, but I mean, in your experience, what would you say? Like, what are you targeting?
The goal, you could say, of my data collection, what I did was mostly to make sure that other likely activities that you're able to do does not trigger it authentically. If you're thinking about kind of an adversarial scenario where someone wants to fake brushing their teeth, I think, for example, kids, or maybe
it's exactly what I was thinking, that if you were to bring this in the market, parents would want to buy this because they want their kids to brush their teeth.
Motivated kids, they are hackers. They are going to cheat your model. But one thing that is very informative, which relates to the previous question about direction, is like the angle that you're holding at. So like this is not a likely toothbrushing motion. So you're going to be, I mean, it's at least very unlikely. So that is some information that the model can pick up and then use. So it will be at least some trivial cases. And also you don't want that your device, if you're, for example, walking with it, don't want to trigger this kind of stuff. So, but angle plus direction, I think it's reasonable for, someone that actually uses it normally. If someone wants to cheat it, they will find a way.
Thank you so much.
I think we're pretty much at the end. I really feel sorry for John's gums with that training set. I really appreciate all the engineering issues that you guys presented. That's really good for other people in the field to realize TinyML is not just loading that model on the device. It's the communication, and it's the multiple different versions of your models and improving things. So great presentations today. Thank you so much, people. I think we're pretty close to done. So have a really good day and stay in touch, you guys.
Thank you very much.
Thank you so much. Thank you so much. Well done.